started.
Hi, so I will start with screen share, the entire screen. Share. Ah, why is it not? Share. Okay, is everyone seeing the entire screen or just portions of it?
Entire screen.
Yes.
Okay, nice. So let me start with this. So so far what we've been doing is we've been saying, okay, and he introduces like that. When in the past, when I wanted to use something like, let's say, linear regression, we will do something like this: the from skip-learn import linear regression, and then do this line. So these two lines just do the linear regression part. But actually, what we're going to try and do today is actually go deep inside in terms of what this linear regression is, when to apply it, and then pretty much just do that for the other ones as well. So first, the problem. So linear regression. No, why isn't it letting me write? Draw. So this is linear regression. I don't have a stylus, so excuse my handwriting. Can you guys still see?
Yes, we can.
Nice. So for linear regression,
You can also type, by the way. That's fine if you want to.
Sure. I will be able to type. So for linear regression specifically, we're trying to, so overall, in any machine learning problem, right, you always have a goal. Oh, insert text box. Where's the text box? Like you always have a goal, and your goal is to
double-click. I'm sorry, just double-click on the page, and you can type. You don't have to insert.
Oh, nice.
There you go.
Yes, thank you. Goal. Thank you. So your goal is to reduce. You always have a goal. So right now with linear regression, our goal is to reduce some cost function, right? And specifically, let's say we have this. Let's say this is our example, right? Let's say we're a team of people and we went on a survey. And actually, I did this recently, and it's sort of like approval of a candidate. Approval of a candidate and number of people. Right? Say I do 1, they say 10. Say I do 2, they say 20. Actually, say I do 3, and then it goes something like this. Right? So we can pretty much see the trend here. And we want to be able to build the machine learning, want the algorithm to be able to build this as well, right? So right now you can all see, like all of us can see, is y, this is our y-axis, this is our x. Y is equal to 10x. So pretty much what we're trying to do is pretty much come up with this formula right here. That's our goal. And our estimates, what we're trying to estimate is this 10 right here. Is this 10 right here. Where's the textbook? Which he tried to do here. Yes. Let me find some else. So say our algorithm, say this is the correct thing, and say our algorithm says 5. Where is the draw? And say our algorithm, say when we predict this one wrongly, and we say it's 5x, then the values would be something like this. Should I have the stylus? Then it will probably come like this. X, X, X. We can see the difference. Can you guys sort of see the handwriting? I'm sorry, I didn't have a stylus with me. But can you guys sort of see the handwriting thing?
Yeah, we can see that.
Okay, nice. So for the first one, we predicted 5x. So for the first one, we said it was 5. I just wanted to first introduce sort of like the cost, just talk a little more about the cost. So the first one is 5, next one's 15, and the next one is 3 times. Oh no, 5, 10, 15, bro. So you can sort of get this notion of the cost if we, wait, how do you scroll down? Nice. So the actual value was 10 in the first one. The actual value was 10 in the first one, and we said it was 5. The next one, we said it was 20, and we said it was 50. It was 10, right? 2 times 5, that's 10. And the last one was 30, and we said it was 15. So now we calculate the difference between these two, just sort of how we get to this equation. What is that? So overall, the cost of anything, the cost function, is equal to 1 over m, just sort of like your mean square difference. This is your MSE square. MSE cost is equal to 1 over m, the difference. So the difference, the predicted value for the first one was 10. Sorry, the predicted value for the first one minus our original, the actual value minus the original. So it's 10 minus 5 squared plus 20 minus 10 squared plus 30 minus 15 squared, and that's over 3 because we have 3 examples. So actually overall, this is our goal. Our goal is to reduce, does this equation, how we got it, make sense?
And it was actually the root of that, but because apparently this cycling or whatever, they do better job without the square root.
Yeah.
So that's why they're doing MSC rather than RMSC.
Mm-hmm. So for typically for linear regression problems, right, you have something that is that's of the form. This is just one very simple example. Typically for linear regression problems, you're predicting something that's of the form y. This is for simple linear regression problems, mx plus b. So for instance, like where I worked over this summer, we did something like we had sort of like a stock market. You want to predict the price. You'd want to predict the price. Let's say you want to predict the price given, let's say, the actual price, given, let's say, days, given what day you have. So it'll typically go in this form. That's where this one is. So he first started off by introducing it with like a very simple linear regression problem where this theta is 0. Just imagine it's your B, theta 1 is your M. And pretty much our goal is to sort of find theta 0 and theta 1. Now there's actually 2 ways you can do that. There's the mathematical, like the very direct way with using the normal equation. Where's the normal equation? Using the normal equation here. This equation is actually quite a bit. So let me write this one down. So let's say we have, let me rewrite that equation because I can't write theta. So let's say we have theta, I think you wrote theta is equal to, I'm not gonna prove this, but I wanted to explain how, I wanted to explain just some of the, what do you call it, art behind it. So he said x minus 1. It's actually, let me pull this.
I haven't. I can just say it's just x transpose x
transpose
x transpose x like minus 1, like
minus
power
1.
of minus 1, and then again x transpose y.
X transpose y, right? This is the equation.
Mm-hmm.
Okay, I'm not going to attempt to prove it, but I will explain why. So overall,
So
right,
the minus one is like after the parentheses.
There's a minus. Wait, there's the second minus one?
No. You put the minus one within the parentheses for the x.
I get what you mean. Thank you. So it's x transpose x and then minus one, right?
Yeah.
So this big X, I don't know if he went into depth with that, and this Y and this theta. So overall, we understand this part. Y is equal to mx plus b, right?
Yeah.
This one, we know this formula. But in machine learning, we don't use this formula. We generalize it because why not? We say y is equal to theta 1 x plus theta 0. And then because we're even lazier, we say y is equal to theta x. And part of the reason why you get this formula is because of this. Is because of this theta is representing a vector. Theta 1 and theta 0. And this one is representing, I think, let me see where he...
The matrix of all the features.
It's representing the matrix of all his features. Where did he talk about that part? Yes, here. Yes. And x1, it's a matrix of all his features. x1 to x1, x0. But we don't actually see x0 because x0 is 1. So when you do sort of like the, what do you call it? Not the matrix product, but the dot product. So there's actually two types of products. There's a dot product and then there's a matrix product. We will use both, which kind of gets confusing at some point. So that's pretty much how everyone understands this part, right?
Yeah, I thought that a dot product, if we just calculate it manually, that's going to give us a scalar value. But ironically, when we use dot product function of scikit-learn, it's going to give us a one-cell matrix, ironically. Although that's, so we are basically, although we are using a function named
I think I see what you mean. So this equation right here, this is one instance, right?
Yeah.
Supposing I give you, this is one instance for one feature. Supposing it's, let's say you want to predict the stock price of, and I give you the day, right? You have theta 1. You have your y, you have your y-intercept, you have your what do you call it? And you have your gradient. You have theta 1 and theta 0. Then I give you some variable, like let's say for the second day, this will just return one value. This is actually giving you one value. This portion right here is one value. You're correct. In terms of the dot product, does give you one value. It does give you one value. But when you now, so in general, this is for one instance, and then this is what you do if you want to do it for multiple instance. Then it becomes capital Y hat is equal to your theta vector times your big X, all your examples pretty much. But the reason, well, he wrote it in a very small way. Does that help? And please let me know if I'm wrong at any point. Please let me know if I'm wrong.
Yeah, that's exactly what you just said. So the dot product higher up was the scalar value, and then this is explaining why he's just changing it to matrix form of it. Just that the output of that function will be a matrix, so we can work on, because with scalar we can't work.
Yeah, and I'll explain something. So supposing you have, let's say, this is until I did this. So supposing you have days, right? Supposing these are your days, and this is the price. And this is the price. We have day 1 is 10, let me not use 10, let me use 30. And day 2, it's 40, I don't know. And then it goes like that, right? So supposing we have actually just 3 examples, and the 3 is 60. So we have our x values would be 1 by 3, 1, 2, 3. Our y values, our big Y, will be 30, 40, 60. And then, oh no, our theta, how do I escape? Let me just go down. How do I zoom down?
You can't scroll. Oh, and there's
can't
no
scroll for
zoom out function. Yeah.
And oh, now it allows me. Okay.
So hold the control and then reuse your mouse wheel to zoom
My
out.
mouse. Thank you.
Typically,
You use Zoom a lot. You use the OneNote a lot.
I do, yeah.
And then our theta would be, let's say we estimate it to be 2 values. Let's say it's 30. What's the actual theta? M is actually 15. But let's say it's 30 and 4. Let's just say. And then just pretty much one thing that always helps me personally when I'm trying to get it is the matrix dimensions, using the matrix dimensions. So if we looked at this, since X is theta, yeah, 2 by 1. So this one, so this example will be 2 by 1 times 1 by 3. Wait.
I thought it's gonna still give you a 1-cell matrix, a 1 by 1 matrix, but it still is matrix, not a scalar value. But it's gonna be 1 value.
There's a way to generalize it. Toby, wait. Toby, do you get what I'm trying to do?
No, I'm just I'm trying to understand what you're doing.
So I'm trying to make it such that even if it's not for one case, where like for the general case, where you get like the big where you get the big thing, where you get the big one is what I was trying to see. Because this is for one case, right?
Yeah.
Yeah. I think where you do like theta is 2 by 1. What did you say? I'm sorry. Let me see. It should be theta. It should be 2 by 1 times 1 by 2, but that would give you 2 by 2, which is wrong.
So can I, before you move on too much, so I'm not sure about the rest of you guys who haven't looked into this that much, but I'm not really up to date with my matrices and how that works. I mean, I remember doing it in like junior high many years ago, but could we like go through, so when we say 2 by 1, you're basically describing the size of a matrix, and then I guess that would make it a little bit easier to understand what you're trying to show, maybe? I don't know.
Wait, I'll come back to that
sense?
one. I'm sorry. I'll come back to
that. Yeah, we can just
which one? Yeah. Because what I was trying to do was pretty much generalize it for this one, because this is the bigger one. This was the, what do you call it? This one uses the matrix dimensions to pretty much like, it backtracks basically from this equation. It comes back from this equation. And I don't know the proof for that one. It's not too complicated, but it didn't really interest me to look for the proof. But yeah, that's what I was trying to do. I'll come back to that one. Maybe with the polling. I remember with the other example, but I don't remember with the simple one. So in this example that he showed, he just sort of like So there's two ways you can solve the linear regression. You can use either the normal equation, or you can use a step-by-step method, which is called gradient descent. That one is more interesting. But with the normal equations, you just sort of like have your values, and then you just use matrix multiplication. He did that here. He did that here. The T here represents the transpose. And then he multiplied it. So our original equation here, y dot T transpose dot the linear inverse of x of everything. That's pretty much what he tried to do here. But he wrote that using a Python script. And this were the values he get. Now this is a very good estimate because the original values of theta 1 was 4, and the original values of theta 0 was 4, and the original value of theta 1 was 3. And you can see that here, the y-intercept is somewhat around 4, and the gradient is somewhat around 3 as well. So this is the,
so let's just address Sina's question about the matrices. Like the way I understand it, that you can just keep it in mind and like try to add to it more while you're reading this chapter. But like either you have a scalar value, which is just it's not in a matrix dimension, but just a value like 1, 5, whatever. Then you can have multiple numbers, and you may want to like keep them all in like consider what they call vector as is just basically one row or one column vector. One row or one column matrix. Basically, vector is a collection of numbers in a different space. And matrix, if you have multiple rows and multiple columns. And you knew them already, but then they're like you cannot. You have to like I guess you have to like Google what how you can just add numbers of the matrix, like how can you multiply, how can you subtract, add, or all those stuff. Those are you have to like visually see them, like just without examples they would be harder. So that's the matrices, and matrices have their own shape, like that's defined by the number of rows and number of columns, and that will define that if you can, for example, if you want to multiply a matrix, meaning a collection of numbers or whatever that you have, to another matrix, which is another collection of numbers and numbers, there are some specific terms. So you can like because there's defined way of doing a multiplication, for example, their shapes need to be in certain definition, basically. And so that's so those are like all the matrix function, like matrix mathematical things that you can do with matrices. But here what they're using is matrix transpose and matrix inversion. These are two separate things. So I had to like review this myself because transport is like super easy, and like you can just change it diagonally, but like the inverse is you have to like Google what inverse is. It has its own definition almost. But now here basically trying to like take numbers, each number, from like a scalar system to a matrix space. So that's why they're adding transpose and like inversion to all those numbers, basically manipulating it mathematically to take to change them to the matrix values. This is how I can explain it. That will help me go through this chapter.
I'm sorry, I didn't catch your question. I'm sorry, but did that make sense?
It does. Yeah, it does. I was just basically trying to kind of, I guess, help the discussion, but I guess we got caught with the numbers and numericals, and I kind of lost the sense of when we went from scalar to the vector and matrix blend. So I thought it would be nice to kind of signpost it. Okay, now we're talking about matrix products.
I got you.
And one thing that I also want to add to that, the linear regression, is that, as Shima said, there is a problem. We have so what we call instance throughout the chapter is basically our data points. So each data that we have, it has some features and it has a target value. So what we want to do is to take the features to the side and take the target value to the side, and from the features to get to the target value. So we put the target value always in the Y direction, and then all the features in the X axis. And then if we plot our data, then either the data is in a linear distribution, then we can fit a line function to that. Line function, we can all remember that it's just like a plus the product of a by x plus some sort of residual value like b or something. Here, instead of b, the residual value, or where the intersect of the x and y axis. So it's called theta 0, and then for the a part, it's just theta 1. And then it's just a simple linear line. If we get more sophisticated lines, they have their own mathematical definitions. But you have to remember, you have to just refresh your mind on what different ways of data distribution is. Is that linear? Is that a polynomial? And they have their mathematical functions.
Mm-hmm. Precisely. Now that's on point. You have to, so you start off with a goal. Every goal in machine learning is to reduce the cost. And before you start, you have your data. So you would have all your instances or all your examples. You can't predict something without knowing what has happened before, or what looks like what has happened before. Which is why with the past, we always spend a lot of time on cleaning the data, making sure the data is as close and as consistent with whatever is coming up. And then from there, you decide from your goal. First, you pick your goal. So in linear regression, our goal is to reduce the RSE, the MSE, is to basically bring that cost to a minimum. That's our goal. And from that, we can get the goal based off the type of problem we have. And then pretty much from there, we start backtracking. So thank you, Elmira, for that one. All right, that was nice. And yeah,
I hope it makes sense to Sina, and all the rest of them.
Yeah, please, if it doesn't make sense, because some of it might be, I might understand it, but explaining it is very different. I learned from professors. They understand something, but explaining is very different from understanding it. So actually, he pointed out a drawback for the normal equation. So the problem with the normal equation, like it says here, is that it's computationally somewhat expensive. So I don't think we've ever talked about, correct me if I'm wrong, but I don't think we've ever talked about big O before, correct?
That computational expense?
Have we ever talked about it before?
No, this is the first time he is bringing that up.
So yeah, and he just chips it here very casually.
Exactly.
He just chips it here very casually. So one way I can pretty much bring up a very nice way of explaining big O is sort of like this. So everyone, I'm assuming, if everyone has a Twitter account, right? And let's say we want to look for Chima's name. And the approach or the way we came up with, let's say since there are 7 of us, yeah, there are 7 names right here. There are 7 names on the participants. And the approach is, let's say we're looking for Stella, we're looking for Stella's name. So you would go to Chima, that's not Chima. You go to Judy, that's not Stella. Go to Sina, that's not Stella. I'm doing it according to my order. It might be different. It might be different for you. Goes to Abigail, that's not Stella. It goes to Toby, that's not Stella. It goes to Stella, that's Stella. And it goes to Naz, that's not Stella. So pretty much we have to go through everything. We have to go through everyone before we actually come back and say, oh, we found that person, right? Or almost everyone. Like supposing Stella was at the bottom of the list. So in this case, the approach that we came up with, right? In CS, we call that big O of N, right? Because for 5 people, we have to go through every 5 person. In the worst case, worst case scenario, we would have to go through everyone, right? But Twitter doesn't have just 5 people. It has thousands and millions of users, right? So you could see how that would be computationally very expensive to go through the entire list, right? Now, this approach is actually quite worse. It goes through the list twice, like squared amount of times. So if it was 5, it would go through the list 25 times, right? It would say, so supposing it wants to look for who, let's say there was another person, like another Chima. Let's say there was another Chima here. So the way I'll try and look for it is once I find one Chima, I would hook on that Chima and then look for the second one, right? Let me see. I would look, why is it not showing? Yeah, I'll look for one Chima, then I'll look for the other one, right? And it does that so a squared number of times. So for, which in CS is really bad. Like that's very computationally expensive. Which is typically.
I thought this one was actually more than to the power, like the square.
It is more than to the power.
It's more than it's 2.4 to 5. Is that 5 point something? But I can't remember if you share your screen. It was like there. So as opposed to what can be reduced to only the square.
Yeah. No, you're right. So it'll pretty much go through it like it will go. Yeah, you're right. It's actually
2.4 to 3. Yeah, there.
So it would go through the list. So if it was 5 people, it'll go through. What's 5 cubed? 125, I think. But it will go through the list a lot more times than it has to, like depending on the implementation, which is computationally expensive. Now, it does have its benefits, like, so computing linear regression using normal equation is very good for very small, for very small sample size. And the predictions are relatively fast, right?
And there will be a good table, like down there when he introduces everything, and he keeps talking about the instance.
Yeah, I like that table when I saw it. He talks about all the gradient descents. Does the bigger part make sense? Especially if it was new to you. It's still something that I partly struggle with in terms of bringing up a solution that isn't as inefficient. But yeah. And the next one is, the normal equation is very direct. Gradient descent is another way we can actually solve the cost. So like I said earlier, right, our goal is to find, this is the cost, and these are our values of theta. And our goal is always to find the minimum cost, right? Is to find, this is our goal right here. Typically the way, and the cost function, because of the squared value, it's bowl-shaped. So because of the squared value, it's around the bowl shape. So one thing you can do, he said if you start from here, and then pretty much the way everyone describes this is sort of like you start from one point. So in gradient descent, you pick a random value for theta. You say theta is something. Let's say you just pick one value of theta. And typically this value of theta will be wrong. you compute the cost, right? You check if the cost is correct. And then pretty much, and then you adjust your value of theta, right? So that you keep going down, so that your cost keeps going down. Does that part make sense?
Yeah, so basically we have data, and we have
Mm-hmm.
our predictions based on those data. And
Mm-hmm.
we are based on those predictions, we are mathematically calculating cost. And that cost, because of the mathematical function of it, because it's just it is squared function, so it will be just looking like this exactly. So
yeah,
exactly. And then next, so our algorithm will try to, there are multiple ways of, and so schema is referring to as solving the cost function, or I've heard like people say like optimization algorithms, like how to get to the bottom of this cost. So the less the cost, the better, right? So our goal is to bring our predictions to the target. And that is one of the ways to do that is to reduce the cost function. The less the cost function, our predicted values will be similar to the actual values. So that's what we are trying to do. And previously we used the closed form or normal equation to do this. Yeah, and then on this one, on gradient descent is, he just used a very interesting, like right here, you have it. Suppose you are lost in a mountain in a dense fog. All you know, you are in a mountain, which is basically like this, and then you want to like see what would be the best step, best next step for you. And then all you have is just sensing with the tip of your toes, just sensing around to like see if your goal is to get to the bottom of the mountain, you would definitely choose the one that is steeper to the hill, like downhill. And if you wanted to like go back to the up, which is not our goal here, you would have choose the other way. But that's like a very good example.
Mm-hmm. I believe, yeah, that was a very very good example. It was a nice one. But yeah, and then your goal is to, so with the normal equation, we got this yellow point relatively easy. Once we just said x dot that equation, we just get this yellow point, typically easy. But with gradient descent, we start off here, and then we come back. Now I'm going to explain the next one is the learning step. So I think we've talked about hyperparameters before, but we didn't really talk about the we haven't really talked about their, what do you call it, like how we get to that one, right? We've only just said input this hyperparameter.
Yeah,
so
learning step is the first one here he's introducing.
Yeah, learning step is going to be the first hyperparameter. So this is, he casually just introduces it here. So a hyperparameter is something, I think Judy has asked this of us before. What is a hyper? Yeah, I remember that. So the hyperparameter is typically something you set. It's not, and in gradient descent, there's actually two, in normal gradient descent, there's two hyperparameters you're going to set. One is the iterations, number of iterations, and two is what we call the learning rate. Now, the way I understand using this example of you're trying to go downhill, the iterations is basically how long you want to keep going for, right? Yeah. How long you want to keep going for. And then the learning rate is sort of like how big a steps do you want to keep. I don't know if you want to keep jumping or like speeding up so that as you're going down, if that makes sense. Right?
Yeah, exactly.
Yeah. And then, so there's two hyperparameters with this. Learning, he hasn't mentioned the second one, but the first one is the learning rate hyperparameter. Now, depending on how you pick the hyperparameter, you can, if you're someone like me, and I typically find myself in that situation, I'll probably want to go down, just because I'm bigger, I'll probably want to go down very slowly. So if I go down very slowly, this is typically what will happen. It's sort of like you can picture it going like this, but we're nowhere close to the minimum, right? It'll just take us a longer time to go to the minimum. It says if the learning rate, then the algorithm will have to go through, that means you have to go through a longer time, which takes a long time to go through. And then, but if the learning rate is too high, like if I'm taking too big a, why is it frozen? If I'm taking too big steps, I can jump and miss it. I can jump and miss it. I can jump and miss it, and then I can jump back and miss it, and jump back and miss it. And I could jump to the other bowl, to the other end of the bowl, and I could miss the what do you call it? I could miss the minimum.
Bottom of the cost function, yes.
Yeah. Again, this is our goal, is to minimize the cost function, and we're using linear regression. Regression, remember, there's two forms of classification. There's two forms of supervised. There's regression and classification. Regression is where you're trying to predict a value like, let's say, price of a house or number of students that will attend your class or something like that. The classification is the other end, where it's like, is this a spam or not? Is this mail or not? Or that kind of question. Does this part make sense? I can't see most people's thing on Zoom, but that's okay.
Do you think we should be pausing and like asking if people?
Yeah. So I'll take a pause. I want to pause. I'll share. I know you could do that in Zoom.
No, just by pausing, I mean, what do you guys think? Does it make sense? Do you have a question?
Yeah, from my end, I think it does make sense. Yeah, it makes sense, and I've been following.
Good.
Okay.
And Sina?
How's everyone else?
Question, I guess, about the hyperparameter is, does the rate have anything to do with the iterations, or is in there two?
Oh, my bad. So there are two very different things. They're
Okay.
two very different. So you set your rate. That's a very good question, actually. So you set your rate as something, as one thing. Typically, you set your rate around 0.3. And then your iterations, it can go from anywhere from 100 to 50,000, depending on what you're trying to model. Yeah, that's a very good question. So you said both very differently. And let's say you notice it's taking too long for the model to achieve to get to close to zero cost, because that's your goal, right? Is to go to zero cost. Let's say it takes too long to do that, then you can just bump up your learning rate by, let's say, 0.5, 0.8, and such. Experienced people know the rate, know how to pick the rate a little bit easier than most. But yeah.
Thank you.
So about that, so sure, just since you're on rate and iteration. So I assume iteration is a number of times it will try to go through and check that, and then rate is rate of what? What are we rating? I mean, what's the?
Oh, I'll explain that one. I'll explain. There's the general equation for it. So with gradient descent, you start off like this. You start off by you pick some random theta, right? You don't know the theta. And then you say pretty much this is where the iterations come for, right? For as long as for this number of times, so we've picked the random data. For this number of times, we set the number of iterations, right? Keep reducing the theta so that it approaches our goal, so that it reduces the cost, right? That's pretty much I think those are pretty much the 3 steps. And the amount you reduce it is determined by the learning rate. I think maybe this part might help. Let me see. I think this part will help. I think this part should help. Where did he do? Didn't he list the algorithm, or did I write it down?
So in the list of algorithms, are you trying to find the table that has all of them, or?
No, I was trying to look for this equation right here. This equation's right here. not stochastic, just batch. Yes. So this is general equation. So pick some random data. Again, we don't know. And if you notice, we're reducing theta, right, by something by, this is your learning rate. This is your learning rate right here. This is what we pick, right? And then we're reducing theta by a gradient. This is why it's called gradient descent, because while you're on the hill or mountain, you're sort of getting a feel, and you sort of know whichever way goes down is going to the what do you call it? Is getting you close to the bottom of the hill, right? And one way you can sort of get the feel for how you're going down is by calculating the gradient, right?
Yeah.
These are sort of like the 3 steps. So initialize, iterate, and then reduce theta so that you can start coming down. Does that make sense?
Yes, it does.
I think so, yeah.
One way that I try to understand the hyperparameters is that you're the algorithm, and you're left randomly somewhere in the mountain, and your goal is to get to the bottom of that mountain, right? So hyperparameters are basically saying that you have like 100 steps to take, and this is your choice to decide how big your steps to be. That's the learning rate, and how many steps you have to take. And your goal is to get to the bottom. You have no idea how far that bottom is, but like the bottom line is away from you. And one thing that's important is that it's not a human being, so you can have like as big as the step that you want. So smallest or largest, you can be conservative, will take such a long time, or you can be just I'm gonna like jump from here to the bottom, like wherever I land, I don't care. And then so these are the hyperparameters, and you can just change them based on experience, as Chima said. But hyperparameters is basically defining your algorithm. Yes, your goal is to get there, but how to get there, like what parameters to choose to get there quickly.
Does that make sense? Sina? Oh.
It does, yeah, it does make sense. I think one of the problems I have with machine learning in general and how he discusses things as fluent as he tries to be is the word choice. Like rate, in my mind, I think of rate differently. I guess he or machine learning uses it differently. So it's kind of understanding what meaning of the word they're referring to, kind of to grasp it. So I guess learning rate, in a sense, if I'm getting it, it's like the how big your steps are.
Yes.
And then iterations, how many steps you want to take to get there. So.
Exactly. So there's some guesswork with with sort of like gradient descent.
Abby, how about you? Does it make sense, or?
If anyone wants, I can go back. We can go back. Judy really wants us to understand this chapter.
Abby? We can't hear you.
Yeah, I get it. I get it. I liked your explanation about hyperparameters is just like taking steps you want to get down, but you just have to calculate what you need to do to get there.
Awesome. And I believe Nazanin should know them all by heart. So if you want to add Nazanin, please go ahead.
No, it's okay.
All right. Yeah, like Nazanin and Toby, you are a pro in this. Please let us know what you think. Otherwise, people can know. But Chima is doing a great job. But for me, Sina and Abby, who are not as experienced as you are, as technical as you are, we don't have that background. So your input will help us learn better.
Nice.
And
sure.
Okay, I have a question to ask. Chima, can you go back to the normal equation?
I do not know how to prove it if that is the
No,
question.
it's not. It's not the proof. So at the top there is the MSc formula.
This one?
Yes. So normally what I understand is it's the y predicted minus the y.
No, the
No,
equation
no.
for 4.
The equation this MSc cost function equation. So
Are you talking about this one or this one?
the MSc x h naught,
This
yes,
one?
that's yeah. So while going through the internet, I read some Medium posts where they actually use 1/2m.
Oh, I'll explain the 2. I understand the 2. So the 2 is sort of like, I get that part. When you take, so our goal is to reduce the cost, right?
Yeah.
Our goal is to reduce this cost. And since we're using gradient descent calls us to reduce the cost by using the gradient of this function. So most people use 2m because because the derivative of this, right, is you bring this 2 back down here, you bring this 2 down here, and then you subtract 1 from this 2, and then you find the derivative of this one with respect to theta, which is x. So typically most people add the 2m. The way I learned it too had 2m. Most people add the 2m so that when you bring the 2 down, 2/2 will still give you 1/m. Does that make sense?
Yes, and also with the formula, the theta transpose x I, what's that? Is it y spread? Because most materials online you'd see probably y the y that you have minus the y that was predicted.
Yeah. So because of the squared, the order doesn't matter too much because 2 squared, like say you predict 4 and the actual value is 2, then it's 4 minus 2, that's 2. And then you square that. And then if you flip it, then it's 2 minus 4, and you square that, you'll still get 4 either way.
Okay,
Maybe I
it's
should
just
use
that
a
it's
different
a bit
example.
confusing because if
Yeah.
we follow through like that, then we won't know that there's like an order to it.
Yeah. Yeah. The one thing I learned is sort of like just find one and stick with it. Even some people don't represent, like one thing we do is sort of like we use each row to represent an example. Where I learned it was the opposite. Like in class, we use each column to represent the example and then the number of features. You can't see me. And then the number of features is sort of like the each row, like right now, the way he does is each row represents an example. But some places, each example comes like this. Each column represents an example. I don't know if that helped or made it worse. But it's just it's sort of like the best way I sort of understood it was just because I was using code. I was looking at code where it was flipped. Best way is just like once you find one, stick with it. That's how I interpreted it. But yeah, I don't know. Did it help?
No.
Yeah. But no, you're right that there is inconsistency. There's some inconsistency with the okay, I think everyone can still see my screen. There is some inconsistency with the notations, which is why everyone defines their own notation. Everyone tries to define their own notation. So he points out one possible problem with gradient descent, which is say we predicted, say our value is here, right? Please take note that this is the lowest point on the hill, and this is where we're trying to go. If we start off from here and we use gradient descent, we'll probably land off around here. Versus if we start off from here, we might level off around here and come nowhere close to here. But then he says
Actually, can I ask a question right there? I'm sorry. Sorry, Jimmy.
Pardon? No problem.
Yeah, I was just going to ask a question. So one of the things that, again, I hate about these graphs is I need to remind myself what the axes are. So obviously the y-axis here is the cost. If you go back to the book, right? And then, so the theta is not a Hyper. Yeah, exactly. So that theta is not a hyperparameter, is it? So that's a parameter. But is that, I know we're plugging those in to reduce the cost.
Yes.
But so I guess my question has been hyperparameter. When we talk about that, that is not theta. And do we see hyperparameters on any of these graphs?
No.
On any of the axes.
I get what you're saying.
Sure.
So in graphs where you would see hyperparameters, like say you want to, like typically where you would see a graph with a hyperparameter, please note theta is what we're trying to get. It's not the hyperparameter. Our only two hyperparameters are number of iterations and learning rate. Now say I try out a bunch of learning rates, right? I try out a bunch of learning rates and I said scroll, yeah. I try off a bunch of learning rates of alphas and then cost. Like let's say one is 0.3, like I said, and then the other one is 0.5, another one is maybe 1, and let's say it comes like this, right? From this graph, we know the best one. Typically, you plot the graph. You know the best one's pick is 0.5. That's typically in cases where you would see where people would start drawing graphs of the of using the hyperparameter. It's just to pick the best one. It's a visual way of you to see the best one.
Okay.
It makes sense?
So again, how do we? I'm trying to make sense of the squiggly of the graph. So obviously it's not linear. I get that. And it has two minimums.
hills.
One is local. One is a global.
Yeah.
I guess I'm still not happy with how my mind perceives the graph.
Is it how graded descent? Are you asking? Is your question how graded descent will solve this?
I think I can get what Sina's question is. So Sina, we have multiple cost functions. One is MSc that will give us the ball shape graph, which was higher up. This is a different cost function. If we use this one, and then we usually don't use such a cost function that will give us not a ball shape graph. So this is our determination of what cost function we want to use. Okay, so the fact that you're seeing this graph is a different thing. So and then that the theta is what we want to get at as we're trying to like find a line with theta 0 and theta 1, right? For a linear regression for a line function. And that's that, and that's like a parameter. But hyperparameter is actually depicted in this graph, and those are pink. Like you have that learning rates, and those are like higher up on the same graph. So they were like your hyperparameter is actually shown here, like there or here. So those are blue things, blue dots are your steps. So those are your so those are your hyperparameters. That is basically he is showing you a cost function, whatever you've picked. In this case, it's just MSc, and on the other case was something that I don't know what it is, but I know that that's a different cost function because we are dealing with a different graph there. But our parameters, theta, that we are trying to get at is at the x-axis, and hyperparameters are shown on this graph by purples with steps and all those like learning rates.
The purples are not the hyperparameters. I think these ones show I thought they show the effect of the hyperparameter you pick.
That's what I'm trying to say. Like that's like the secondary way of showing the hyperparameters.
Got it. Cool.
He was just trying to say with this graph that fortunately, right here, fortunately, this is not how we'll encounter this problem with our specific cost function. He was just trying to.
Shima, I have a question. What kind of cost function was it? Does it have a name? What is that? What is that? No, not that one. I know that one. That's like
this one?
Yeah.
Oh, this is just a random cost function.
Okay.
I don't know I don't know the name. I think he was just trying to point out a counterexample of where gradient descent would be wrong.
Yeah.
Of like pitfalls, because he says no. So this, one thing I didn't like was sort of like how he jumps from this to this, right? So one way you can picture this is not this graph, that's a bad example. This graph, right? In this graph, we're only predicting one theta value, right? So we're trying to plot costs against theta, either theta 0 or theta 1, right?
I thought that was a vector of thetas, meaning all of them.
This one?
Yeah, I think the x-axis is the vector of all the thetas that we have. In this case, is 0 and 1, right?
I thought if you want to picture, I thought you use like a 2D thing if you want to picture two things. And then this one is sort of this was the, what do you call this thing again? Or am I wrong? I think I might be wrong with that. Like if you want to picture, this is sort of like a 3D, I can't remember what they call this thing.
No.
Contour plot. Or is this a contour plot or am I wrong?
That makes sense.
You get what I was trying to say, right?
I do. Like, I think that makes sense. On the first graph, both theta 1 and theta 2 was depicted as x-axis. Now it's just breaking that x-axis to two separate dimensions, which is theta 1 and theta 2.
Yeah, that makes sense. Yeah. Yes. Yeah. Let me see if I can. Is this what I think he's trying to say? So originally we have theta 1, right? Theta 2.
Perfect. You're doing that exactly what you should be doing. Exactly. Yeah.
Yeah, and then the cost.
Mm-hmm.
And then.
Like put a cup in there.
I'm sorry I'm so sorry for this if it looks awful.
That's perfect.
And then, so with the first figure, he was sort of seeing it like this, right? He was looking at it like this. And with the second figure, he's looking at it like this. Does the drawing make sense?
That's like the best way of depicting it. Does it make sense to everyone?
To everyone that's not
here. Yes, it makes sense.
Yeah.
Right.
Yeah. Sina, did the drawing help or no?
It did. I actually kind of made sense. I guess looking at the coffee cup one, the circles, it's like the other axis kind of coming out at you or into, I guess, the page. So that would be the third axis you draw, which we drew, which really helped. Yeah, that was nice.
So this is the first one he did was sort of using a contour plot. With a contour plot, let's say with a contour plot, we have the blue one, then we have the red one. And then we just look at it like that, and then we just say theta, no, it shouldn't be red, but theta 2, and then we just say, okay, we've seen the green one. And then we'll see the blue one. And then we'll see the black one. Yeah, that's just sort of like how he looks at it from that angle. And one thing the reason for these two distinctions is, if you guys remember feature scaling, try to get all your features to be around the same, what do you call it? Around the same scale, or around equal dimensions. Basically, what that means is sort of like, let's say you're trying to predict a house based off the square feet and the income of the household. Income will probably be around the hundreds and thousands of dollars, but the square feet is around 3,000, maybe around 3,000. So feature scaling, you're just trying to reduce and bring all of them to the same scale on possibly around between 1 and 2, if that makes sense. Yeah. And he says, like, if without feature scaling, this one is the example without feature scaling, like where one feature is maybe like drastically a multiple in the multiples of range of the other one. Then it says gradient descent will still reach it, but it'll just take a longer one. As you can see with the, when you look at the, what do you call it? Yeah, it'll take a long time. It'll take a long time. So far, I want us to do the pause thing. So far, how is everyone feeling? Does it make sense? Does it not?
It makes sense. So one thing I would think would be a great thing to do, so Dr. Cho said to kind of stop us at 1. But I think one thing that will, when we're done with this chapter, help immensely is kind of try to summarize everything in like a 5-minute quick summary of like the major points to kind of bring it all back together, because it's a lot of stuff that he's kind of dumping on us, obviously. But so far it's making sense, like breaking down stuff helps.
Okay. Thank you. I'll try and do that. I have that in sort of like my phone notes, but I can try and share that if maybe that'll help. I have that. So overall, right? Overall with, let me stop sharing. So overall with gradient descent, you're sort of like, I think, does everyone sort of get that general gist of pick a value, initialize with theta, and then for these many number of times, or like Mira said, for these many number of steps, right? For these many number of steps, keep adjusting your value of theta till we get to where we want. So far, does everyone get that? Right? Nice. That would lead us to, let's share screen again. That would lead us to this next part where now, okay, there's 3 forms of gradient descent. There's batch, there's mini, and then there's stochastic. Now, where they all differ is sort of like where you're picking how much of the X and how much of the, like, so out of your total training set, right? You have a total training set of, let's say, you have a big training set, and pretty much so we batch. Does someone understand? Oh, with the batch, you're using your entire training set. Oh, no, what happened? 1 second. Okay. Okay. Yeah. So again, we'll need to implement this theta j. Did everyone understand the theta j? This notation right here. I noticed he didn't explain it as much. So theta j is just sort of like your theta j will be theta 0. Those theta zeros that we were predicting before. So the first one will be theta 0. The next one will be theta 1. And with more thetas that you'll be predicting, you'll have more. So in our case, we want to predict theta 0. And this math is pretty much, if you understand how to do derivatives of the original cost function, should be relatively, of the original MSc cost function. Where am I? Of the original MSc function.
It's gonna be 1 minus 1 sigma y hat minus y to the power of 2.
I missed it. I'll leave that one. Okay, that math I actually did understand. Let me see if I can try to explain. His graphs for those ones too. Okay, I'll just start from there. I missed it. Okay. So in general, we have, so we estimate, we start off by giving these two values, theta 0 and theta 1. And these are represented by our theta vector. These are theta 0 and theta 1, right? So in gradient descent, we pick random values for these. And for the number of iterations, we say theta, let's do theta 0, is equal to theta 0 minus our learning rate. I think you represented by alpha, minus alpha times the gradient of, let me just type this. So this would be the gradient, that's too small. This would be the gradient of the cost function with respect to theta. With respect to theta 0, right?
Yeah, I think he didn't use alpha, but he used some like some eng.
What did he use?
It should be higher.
Oh,
right
yeah.
there. Yeah, that thing.
What did you call it? I didn't know.
Eng? Like, what is it? It looks
Is
like
it
ing. No, yeah.
Yeah.
I'm not sure how it's pronounced.
So first we start off by initializing this one, and then we say for number of iterations we pick for, let's say number of iterations is n, for n number of times, theta 0 is equal to that, and the same thing, theta 1 is equal to theta 1 minus the gradient of the cost function with respect to theta 1. That is what we are trying to do right here. That's what he was trying to do. Does that part make sense? Can you guys hear me?
Yeah, it does.
Yes, it does.
Okay. So with batch gradient descent, right, what you sort of do is you use the entire, I'm trying to look for, you calculate you calculate, okay, so you basically use all your data. I was looking for where he said it. I think he maybe says in the other ones then. So you basically use all your X data to calculate this gradient. That's typically all that's changing in the 3 versions of gradient descent. This general step is the same. The only thing is with batch gradient descent, you use all your X. If you notice, he uses all of his XB, which is all of his XB, right? In stochastic gradient, he'll only use 1x. Stochastic, I don't know what the term actually means, but
haphazard.
Haphazard, really? That explains it. Yeah. But with, if you notice, nothing really changed. We picked the random internalization. The only thing is we're picking one instance. So for instance, let's say we want to train using everyone in this group, using something we know on everyone in this group. With batch gradient descent, we'll use everything we've learned from everyone. With stochastic, we'll pick one person, Judy, and then adjust the theta that we picked originally based off Judy's. And then we'll pick another person, like Sia, and then we'll adjust it based off that one. All right? Does that part make sense? The code for it is sort of like he's picking, so we have a total of 5 people. Imagine this is 5, right? Imagine this is 5. And then we say, okay, pick one random person from that 5. And this is basically just indexing that one person out. Yeah, and then pick the Y, and then make your adjustment based off that one person in the group. Does those two make sense? Before I go to the third one, does those two make sense?
So the batch one is the one that for the next step, our algorithm is trying to like figure out what next step to be based on all the instances. So it's calculating all the gradients together and like putting it like in a vector of gradients. And then based on that is trying to figure out which direction to go. But with the other one is just picking a random one, picking a random instance, and by the target value of that is just defining which direction to go. But it turns out that it is, although you would think that this is something that, oh, how random things would help that. What if he's for the next decision, for the decision making, what if it's picking up an outlier? But apparently, apparently it's gonna like turn out very well, and it's gonna save time also.
Yeah. Yeah. Does it make sense to everyone else?
Yes, and stochastic means randomly. You choose the data randomly.
Mm-hmm. Nice. I didn't actually notice, but we're getting off on time.
Yeah, maybe like we can do the mini batch and then close off here. How about that?
Okay. So one thing you can definitely tell with batch gradient descent is like if there's a lot of us, if there's a lot of people, like we're training on, it becomes very hard, right? It takes a long time, my bad. It takes a long time to process everything at once. But with stochastic, it's quicker to get results. It's quicker to get results than the, the other thing than as compared to batch. The one thing with stochastic is since you're basing it off every example, it sort of goes around. It doesn't really hit the minimum. It just sort of hovers around the minimum, if that makes sense. Yeah, just sort of hovers. I think who said stochastic means, I figured it meant something. It means random. And that's pretty much how it looks. Yeah. Now the last one, which is probably going to be our last one for today, is batch gradient descent, where you use, instead of using all or just one, you pick some, like rather than training on all 5 of us, or training based off one person, or making adjustment based off one person, you pick maybe groups of 2, right? And you sort of train the algorithm based off that. So with batch, as you can see, batch smoothly levels in. With mini batch, it behaves sort of as a mixture of stochastic and batch. The advantage is that it's relatively quicker than it's relatively quicker than batch, but also with stochastic, it makes adjustments as necessary. It can make adjustments quickly. And yes, this is, before we go to the next one, this is where So again, yeah. So we've talked about linear regression, simple linear regression so far, where we're only estimating we're only estimating 2 parameters, sort of like the whole y is equal to mx space. And we've used normal equation, which is off the bat formula. Then we've used gradient descent, right? And we've seen 3 types of gradient descent: batch, stochastic, and mini. Right? Does all this make sense? This will
Yes.
yeah. We can do the other ones next week. I can cover the other ones next week. I'll finish it off next week. But for now, does anyone have any questions?
Yeah, so from the last page you displayed, there is a tab called out of core support. And I think we treated them out of core. That was chapter 1, where we said for, I don't know if this is right anyways, but for online learning, it happens
Yep.
online, and then for out of
Yep.
core learning, it happens offline, but it's very similar to online learning.
Mm-hmm.
So now they put for normal equation, there is no, it doesn't support out of core. Can you explain all this? No, yes.
So stochastic and mini, I think out of core. We talked about out of core when we were doing the
Go on.
the chapter 1, right? Out of core, does it have to deal with online learning?
Out
I
of
think
core
so.
is similar to online, but it happens offline.
It's similar to offline. It's similar to online.
It's
So
similar to online, yes.
I'm guessing because the reason why these are no is because all 3 of these require the full data. Like they require all the data, all the examples to be ready. That's sort of why. Yeah. All of these require like the normal equation. It won't work very well if you only give it one instance. You have to give it everything. Like it's for all your big X and then all your small x's as well. It wouldn't work as well without that. I think that might be why.
Yes, and I agree with you, because even when we discuss the out of core learning, it takes in the data in batches.
Yeah.
So and it's
Yeah.
offline again. So if we have these 2 properties of out of core, then I think normal equation, SVD, and batch GD, since they take in the data at once, not in batches, then doesn't support out of core.
Yeah. Yeah. Does anyone else have any questions? And sort of go down the list. Sina?
Well, I have many questions, but I think for the scope of today, you did a great job trying to break it down. I appreciate you taking the time to try and explain. It was good. I think again, the things we discussed so far are kind of clear, but when we're done with the chapter, I guess as you were doing like for the past few minutes, it's nice to kind of go and tie them all together. But overall, great job.
Yeah. Almira, I think you get it. Abigail.
Yeah, I think you explained good. I understand. Oh, sorry.
That's okay.
I understand the different batches, and I liked the example that we gave about like hyperparameters and gradient descent, explaining that. I got it.
Nice. Toby, I feel like you get it.
So from my end, you did a wonderful job, and I just even realized that it seems like I breezed through the chapter, because there are some things that I'm just saying for the first time. I'm like, I thought I read this chapter, so I actually think I need to go back and try and understand what you've said, like more practically, and try and relate it, try and find out how I can connect it to my environment, so I can explain it better, because there are some things that I can't even still explain, but then it seems like I understand.
Yeah,
but I can't,
same. I
explain.
feel that. I feel that. Nazani, you have anything to try or?
No, thank you for your explanation. And I think this chapter is really valuable. We can learn things deeply, and in the next chapters in the future, we can learn how to code with cross and using these techniques.
Elmira, and then Judy. I don't know if Judy will.
No, I think she's not here. No, I just want to thank you. You did a great job. This is like a hard chapter. Like even you just, even we're listening to you and we just read it. It's just hard to remember what it was. So trying to explain it is just even way harder. And that the three-dimensional space that you created. So that was perfect. Awesome job. But try to do that with when we gonna go to the multinomial one with like multiple parameters, multiple theta. Try to do that.
Yeah, I think he explained it. He said he made a side. I don't know if he intended it as a joke, where he was like finding the optimal theta in the 300 dimensions is difficult, but you can't draw anything beyond 3 dimensions, which is
exactly.
So, okay. I think we'll keep it with time today, and then I'll pick up the rest next week.
All right. Thank you.
Thank you guys.
Thank you. Have a good
Thank
weekend,
you.
everyone.
Thank you.
Bye.
See ya.
Bye.
Bye, guys.
Bye.
Bye.